Unfortunately, that can happen with contractors and whatnot. So my neighborhood, they replaced all of the internet with fiber, and so that it was all buried, right? And so in everybody's yard, they have a line that's buried, like maybe from the front yard to where the box is, and they're supposed to bury it like 6 inches below the ground. And these folks had buried it maybe like that much below the ground. My next door neighbor, he went to aerate his lawn, he snapped my line. He felt so bad. So it's not your fault, you didn't do anything. So
Sometimes I just wonder like what's going through their head when they do something.
money, that's what's going through their head. The faster they can do it, the more money they can make. Like, that's actually an easy question to answer.
True.
Okay, everybody. I know I said today I was going to talk about wind, and I'm gonna maybe kind of talk about it a little bit. But I was looking at my notes, and I kind of want to cover wind and seismic, and I kind of think that might take 2 days, and I'd rather do them back to back, like a Monday, Wednesday type thing. So I wanted to talk about some more practical applications, and one element in buildings that we haven't really talked about yet is bracing. And I'll tell you that for most routine design, we did have an example a while back where we had looked at the structure as if it was a truss, and we had just looked at the bracing elements inside the truss and designed those as a tension members. So we had done that. But one thing we didn't talk about were threaded rods. And threaded rods are a very common cost-effective alternative for bracing options, particularly in buildings that are pretty short. And one of the things that had inspired me to do this, so if you go to a lot of low-rise or metal building manufacturing processes and whatnot, you'll find a lot of places like, for example, the PepsiCo distribution center that they opened a couple years ago on Route 60 between Barbersville and Ona. Does everybody know where I'm talking about? So that was basically a big portal frame metal structure, and they're using threaded rods as the lateral bracing elements. My daughter recently went to a birthday party with some friends of hers in kindergarten, and they had it at the the gymnastic place out in Kinetic Park. You know what I'm talking about? And I think they were using that type of bracing there as well. So it's a very common bracing element, and the design of them is really easy. And so I thought it would be a good thing to talk about. I don't have any homework for you today. I'll probably assign something Monday, but nothing this weekend. So it's almost like you all have some projects that you're working on. So, and it's not like you haven't done enough homework for me, So, okay, did everybody get the code? All right. Now, my apologies because that's the wrong presentation. My apologies because we are going to begin our discussion today with something a little grim, but whenever you talk about threaded rods in a structural steel design class, you will invariably mention the Hyatt Regency walkway collapse. And so I do want to talk about this a little bit today. Has anybody heard of this before? Is there anybody that's heard of this? Okay, I've got one person. A lot of people, though, might not have. So like I said, this is a pretty dark day in American history, and a dark day in the engineering landscape, to make a point. So this was a structural failure that took place in the early 80s in Kansas City. And the failure concerned the collapse of this elevated walkway in the lobby area of the Hyatt Regency Hotel. And this was a pretty bad day on the news, for sure. Just to sort of make the point, this was an event that resulted in over 100 deaths and over 200 injuries. And to date, it's the deadliest unintentional structural failure in American history. And more related to us is this is the deadliest structural failure under normal operating load conditions. Okay, so just to sort of paint the picture of what I mean by that, I imagine most of you have probably heard of the terrorist attack on the Oklahoma City building. We just hit like our 30th anniversary of when that occurred, actually a few days ago. When that event happened, so just to sort of paint the picture, for those of you who aren't aware of the details, what had happened was there was a sort of like a U-Haul truck, like a Ryder truck that was parked next to the building, and the truck was filled with explosives. It was filled with homemade explosives. And when the truck exploded, the truck was parked right next to the building, and the columns experienced what's called a Brisson's failure. And to explain what that is, essentially the columns shattered. The concussive force from the explosion was so great that the columns shattered. They reported broken glass in windows in Oklahoma City from up to a mile away from the explosion. Okay, so there is no universe that a structural engineer could design a column in a building for that type of event. Like that was going to be unfortunately, like if you park that much explosives next to a building, right next to the exterior column, that's going to be a bad day, and there's not a lot you can do about it. That's, in fact, like if you look at federal buildings nowadays, like for example, the one down here, see the posts outside the building? That's what those are for. They're to keep vehicles away from the building, a safe zone essentially, to mitigate any of those concussive forces. That's why they're there. So just to put that on point. So yeah, what happened at Oklahoma City was certainly not under normal design loads. This was under normal design forces. The walkway collapsed under the forces that it was designed for. Okay, that's what made this really a harrowing day. To talk a little bit about what happened that day. This is sort of this is an event in history, so you can find a lot of information about what happened on the collapse that day. But this is just sort of a cross section or an elevation view, I should say, of the lobby. And so this was in a urban environment. And so this was a Friday night and in a big hotel lobby. If you've ever been in a major city and go to a big hotel lobby on a Friday night, Saturday night, chances are there's events going on, there's parties going on. And so they would have these regular events in the lobby, and they had this sort of like jazz party, tea dance event type thing going on that day. And so this atrium was huge. There's like 1,000 people, 1,500 people in the atrium. And so the lobby had these suspended walkways. And so what had happened was, there were people dancing, and hanging out on the lobby area. There were people dancing on the second floor skywalk. There were people dancing on the fourth floor skywalk, and whatnot. Well, right here, there's this. The detail of the as-built connection is shown right here. And what had happened was, you've got these people here. You've got these people here. What happened is that this connection sort of like shear failed like that. And so what had happened was, actually let me go back a slide to just sort of make the point. Again, not trying to be grim, but just trying to explain what happened. So when this connection failed like this, what had happened is not only did like the first walkway fall, but the second one did, and they sort of fell on top of one another. And so unfortunately, a lot of the people that were on the second floor skywalk were not only trapped, but there was a 6-inch concrete slab getting ready to fall right on top of them. So there wasn't much that could be done. Now, that's what happened. Let me talk about why it happened. And I wanted to sort of take just sort of a side discussion about structural failures in general. The truth is, when people ask me about engineering and they ask me about the gravity of what it is that we do and how important what we do as engineers, how important what we do is. One of the things that I'll say is, one of the differences between a structural engineer and a surgeon is a surgeon can only kill a person one at a time. a somewhat cheeky way of making a very important point, which is that what we do has a very grave impact if it goes wrong. But one thing I'll say is that if you look historically, just to sort of take a cross-section over the past, 50 years, a lot of times what you'll find is that the reason for structural collapses and structural failures is less about some, how can I put this? Like, we didn't understand a given phenomenon about structural engineering, or we had some grave calculation error and whatnot. We produce designs that should be subject to the scrutiny of independent review. So more often than not, it's usually not the math or the engineering that's the culprit. Often it's the communication, okay? So what had happened on this job was the engineer that designed the suspension system that would suspend the walkways designed them like this, okay? And so the idea would be is that there was a single threaded rod that would hang from the ceiling, and then essentially there would be a nut for the 4th floor and then a nut for the 2nd floor, okay? And so the contractor who was responsible for erecting the frame and erecting the structure took a look at this detail and thought, well, that's kind of a pain. And I could understand admittedly how, think, in order to get that 4th floor skywalk, there, it might be kind of difficult to think, what am I supposed to do? Lift the 4 floor beams from the 2nd floor all the way up and then spin a threaded nut, 2 stories high. So what the contractor did is says, well, I'll tell you what, instead of doing this, why don't we just cut the rod in half and have 2 threaded rods, one going from the ceiling to the 4th floor skywalk, and one from the 4th floor skywalk to the 2nd story skywalk. And I mean, the contractor saved about $20 per each connection. So I mean, we're talking very, very serious money. I'm being very sarcastic when I say that. But the problem was physics, okay? And so what happened was, by changing the configuration, what had happened was they doubled the force on that element, and so the actual beam, the beam here, you would think it was like a square tube or a rectangular tube. It wasn't. It was 2 channels that were essentially welded together. So what had happened was this essentially ripped through, and so you can see this is a forensic photograph that was taken of the site, and you can see here's the beam cross section here and here. There's this, and you can see where the rod just sort of shot right through. Okay, and so yeah, this was a pretty bad day. But again, it was ultimately a lack of communication. It wasn't that we were opening the spec and the spec didn't account for this problem. I mean, if they'd have followed the spec and checked with the engineer and performed all these appropriate quality assurance and quality control on the job, this wouldn't have been an issue. The contractor changed the design. The contractor should have called the engineer and asked, is this going to be okay? And what the engineer would have done is about 10 minutes worth of math and found out, no, it's not okay. Or if you want to do it, we're going to have to use a different beam or some sort of different detail in order to make it work. I imagine the contractor probably had a good point, which is that this actual construction was probably more constructible, that this would have been difficult to erect and this was easier to erect. So that's what the contractor was thinking about, just getting the building erected. But if they had picked up the phone, that would have been a very sad day would have been avoided. So I know that's kind of a grim thing to talk about, and maybe a somewhat grim topic to semi-close out the semester. But I do think that it's kind of important that we take stock of the fact that at the end of the day, what we're doing is important and has great consequences. A lot of times we get worked up over when do we add an 1/8 of an inch to the bolt diameter to get the bolt hole, and when do we add a 1/16 of an inch, and we kind of forget about stuff like this. So it's kind of important to bring it into perspective. But I do want to talk about the design of threaded rods. Threaded rods themselves are fairly easy to detail, but let's just sort of talk about them in general. I don't want the events that happened in Kansas City to say that there's an issue with threaded rods. There aren't any issues with threaded rods at all. Threaded rods are fine. They're a very lightweight alternative for tension members. They can be, I had a couple images that I pulled up here off the web just to sort of make the point. So like I'm sort of talking about, at least for today's application, I'm sort of talking about applications like this. So for example, if you have a metal frame that serves as the framework for some sort of warehouse type facility, which is a very common application for the use of structural steel, you will often include something like these lateral bracing elements in order to withstand wind forces and things like that. Now, one thing I'll mention is that when you look at this bracing system, and I've got another image sort of like right here, you notice that there's two braces. There's one going this way and one going this way. But in design mode, we really only consider one of them, because if you think about this like a truss, so imagine here's this bay and this bay, and imagine pushing on the frame this way, and imagine this X-style frame is acting like a truss. What that means is that one of those members is going to experience tension, and one of those members is going to experience compression, okay? The element that's in compression is really not going to have any contribution at all, because we're talking about this highly slender steel rod. It's going to buckle like a piece of wet spaghetti, okay? That's the reason why we have two of them, because the idea is that if the wind is going this way, then this element is in tension, and if the wind is going this way, this element is in tension. So we put both of them there so that no matter which way the wind blows, there's at least one of those threaded rods in tension. So in design mode, we design assuming one of them's there, even though in reality, we would probably install two of them, okay? Does that make sense? Okay. All right, so two common applications are for diagonal bracing, and then also what are called sag rods. So the idea is if you have elements in a building, let's say going this way and this way and this way, maybe sort of horizontal elements serving as framing, let's say for putting up drywall and whatnot, you might also hang some threaded rods to prevent those elements from sagging too much under their own self-weight. So those are other applications of them as well. We're going to look at them for diagonal bracing though today. Now, if we go back to tension members, remember tension members had gross section yielding, they had net section fracture, they had block shear rupture, they had slenderness. We only have one limit state that we're going to need to assess, and that's net section fracture or tensile rupture in the threaded region. Okay. I can at least explain a few of those. So first off, block shear rupture really wouldn't make any sense because there's no connection region where we would rip out part of it in shear, part of it in tension. It wouldn't really apply to some circular threaded rod. Really wouldn't make any sense. As for gross section yielding versus net section fracture, so we think this is the gross area, this is the net area. The net area is obviously smaller, right? So, and we typically, so we'll assume that the threaded rod is about the threaded area is about 75% of the gross area. And so based on the materials that you use, you can pretty much see that the tensile rupture is only one that's going to matter. Now, ultimately what you'll do is the goal is to calculate what is the required diameter. And so if you calculate a required diameter of 0.489 inches, you're not going to go to Home Depot and buy a threaded rod that's 0.489 inches. You're going to round up to the next available increment, okay? Threaded rods tend to come in bar diameters ranging anywhere from 1/4 inch to 1 1/4 in increments of 1/8 of an inch, so like 1/4, 3/8, 1/2, 5/8, so on and so forth, all the way up to 1 1/4. After you get past 1 1/4, they tend to be available in diameters from 1/4 inch up to 4 inches. I don't know that you would need a 4-inch diameter rod for a bracing configuration, but that's about the commonly available sizes. So what I would imagine most of the problems that you would be dealing with for most common structural applications are in this range. So I would just probably think in design mode, round up to the next 1/8 of an inch increment. That's what I would think if I were you. Now, these are treated as connecting elements, so they're going to be governed by Chapter J. If we go to Chapter J, we're actually using the equation for bolts. This is actually the bolt shear equation. But if we go back to the spec, this equation worked for bolts in shear and bolts in tension. The bolted connections we primarily deal with in steel design are bolts in shear. But this nominal limiting stress could be FNV or FNT, okay? And for threaded rods, it's been a while since we've looked at this table, but if you remember, when we were first trying to ascertain whether or not, or how do we compute the thread or the shear capacity of a single bolt, we would ask ourselves, okay, are the threads included in the shear planes? Are they excluded in the shear planes? What group are we looking at, and so on and so forth, okay? But we had made a comment a while back where we said, okay, the shear stress is obviously affected by whether or not the threads are included or excluded. But the tensile stress is not affected by whether the threads are included or excluded from the shear plane, because we're not talking about shear, we're talking about tension. So there was just a single nominal tensile stress, and it didn't really care about whether the threads were included or excluded. Now, we're not looking at bolts, okay? We're just looking at threaded rods, okay? So we go right here, and our threaded rod nominal tensile stress is 75% of FU, okay? So if we look at a threaded rod and we say, okay, phi is 0.75 or 3/4, okay? FNT is 0.75 FU or 3/4 FU, and A sub B is pi over 4 dB squared. So phi FNT AB, I can recalculate that and get this. I can calculate the capacity of a threaded rod pretty easily by just saying that phi RN is 9 pi over 64 FU dB squared, okay? Where does the 9 over 64 come from? It comes from 3/4 for our phi value, 3/4 for this, that FNT is 3/4 of FU, and then there's a 1/4 because it's pi over 4 dB squared. So 3/4 times 3/4 times 1/4 is 9 over 64. And so 9 over 64 times pi times FUBD squared, okay? Now, to be honest, we're actually not really going to calculate this very much, because if we're in design mode, we don't really care so much what the capacity is as we do, we want to know what the diameter is, okay? So how do we get the diameter? We just solve, okay? We just rearrange and we solve for what is the required diameter. This equation has a little bit of serendipity to it, because if I rearrange everything and I solve for dB, I get dB squared is this fraction times 64 over 9, and 64 over 9, if I take the square root, is 8 over 3, so I can factor that out. So I can calculate the required bolt diameter pretty easily as the square root of our applied load divided by FU times pi, square root of all that, and then it's times 8/3. So that just comes from the algebra. So if you want to design a threaded rod, it's pretty easy. You just determine the factored load, compute dB min, and then select the rod diameter. It's a really straightforward enterprise. And then again, for the available, I'll say the available rods, just go in 1/8 of an inch increments up to 1 1/4, go up 1/4 inch increments past that. Okay, does that make sense? Okay. Now, one thing I haven't talked about is slenderness, okay? Do we have to apply any limits to slenderness? If this is a tension member, do we have gross section yielding, net section fracture, block shear rupture, slenderness? Do we need to worry about slenderness? No, okay? If you remember, for tension members, there is no maximum slenderness limit. Like, it's not actually codified in the spec that there's a limit, but there's a recommendation that the slenderness ratio should not exceed 300. Remember, we use L over R less than or equal to 300 for tension members. But note, this suggestion does not apply to rods or hangers in tension. And the reason for that is because threaded rods are inherently slender. Like, they're going to be slender regardless. They're almost sort of designed to be slender. So as a result, we don't really need to worry about applying slenderness limits to threaded rods, okay? So again, we really only have the one limit state, and it's a fairly straightforward calculation. So to sort of make the point on how to do this, I want to take a problem that's somewhat more reflective of what you might see in the real world. So I want to select the most economical rod, not road. This isn't CE 342. That's supposed to be rod. All right. Select the most economical rod, threaded rod of A36 steel to act as the diagonal brace for the truss shown. Now, I'm only showing one threaded rod, but in reality, you would have another one here. But for the purposes of structural analysis, We are only going to assume that one is present, okay? Now, we have a load applied here. We have a dead load and a live load. This could be dead and live. It could be dead and wind, okay? I want to talk a little bit more about wind on Monday. How we handle wind and how wind has changed from spec to spec is worthy of discussion. So we'll talk about that then. But we're going to assume that the left support is a pin and a hinge and the right support is a roller. So with that, let me go ahead and just jump right in. It's being difficult with me. That's okay. Okay. So the problem that we've been given, so first off, let's look at our factored load. So we were given P dead of this. Is that, okay? And to be clear, what I'm saying is that the 3,000 pounds and the 7,000 pounds are what are applied to this point right here, okay? So I think by now we should all be in agreement that this part should be easy. Fair point? Now, is that what I designed my threaded rod for? Why are you shaking your head no?
Sweep an angle.
And what does that mean?
It means not all of that force is directly in tension with the rod.
And, well, but how would we figure that out? Not quite. What I'm saying is this. That this frame is a truss, okay? And this frame is a truss with a factored load of 14.8 kips right here. We need to know what the force inside this element is. This is a plane truss analysis. This is last semester. This is CE 312, right? So we need to figure out support reactions. We need to figure out method of joints, all that. So is there trig involved? Yeah, there's trig involved, but we're not, that's not really quite what's going on. Okay, so this was 20 foot by 15 foot. So that means that the this is going to be at a 3 to 4 slope ratio. One of our favorite slope ratios from last semester. Because if this is a 3 and 4, that makes that a 5. Okay. So just to put some letters to this. Okay. How many support reactions do we have at A? 2. We're going to have an AX, and we're going to have an AY, and we're going to have a single BY right here, right? Okay. Now, of these reactions, which one should we start with? Which is the easiest one to start with? 2 verticals, 1 horizontal? Maybe the horizontal, right? And what is that horizontal going to be?
14.8.
There we go. what are these since we have no vertical loads?
Zero. Equal and opposite.
That's the right answer. I pulled a sneaky with you on that one. There's no vertical load, so there's zero, right? No. Okay. Here's my point. The 14.8. Okay, so let's think about this. Okay, so let's just think of the structure as like this blob, right? Okay, I have a 14.8 load right here and a reaction right here, right? Okay, like let's just look at these two, right? So they are wanting to rotate the structure like that, right? Like if I grab the steering wheel and I grab my hand this way and my hand this way, I am turning the steering wheel, right? So these have to turn the steering wheel the other way, right? So I need something to turn the steering wheel back that way. I need sum of moments to be equal to 0. So in order for that to be the case, I need this one to go up and this one to go down, right? Okay? Now how do I get those? Well, what would be an easy way of solving for By? Maybe summing something here, summing moments a day. What happens when we sum moments a day? Let's see what happens. So, do I need to consider AX or AY? Do I need to consider BY? At a moment arm of? 20 foot, right? Because it's that way, and it belongs on this side of the table, right? Okay. What about the 14.8? Does it generate moment? The other way, right? At a moment arm of? So 14.8 times 15, that's 222. That's 11.1 kips going up. So therefore, here I'm going to move this over. Well, I could probably just do it like this. If I have 11.1 kips going up, I'm going to have AY as 11.1 kips going down. Okay. Does that make sense? Now, all right, so I like using the method of joints. I find it's easier to use and easier to remember from the past than it is the method of sections. Could we analyze joint D right now?
No.
Why can't we analyze joint D?
Too many unknowns.
There's 3 unknowns flowing through joint D. There's 3 members. And so starting with joint D, probably a bad move. Let's see if I can test your memories a little bit. Can somebody tell me what's going on with joint C? I have a joint out in space with 2 members connected to it, and I have no external loads. So just as a matter of structural assessment, those are 0 force members. Okay. Now we can actually solve the whole truss right now if we wanted, but let's look at member BD. What's going on with member BD? If we look at joint B has 11.1 kips going up, so we have to have 11.1 kips going down. So this member is 11.1 kips in tension. That's gonna be compression, right? Think about it. Like if I have a column, right, and I have 11.1 kips pushing up, The column's pushing down, right? Right? So that, like, what's happening is the ground is pushing up, so the column's in compression, okay? Now, if we ignored the fact that we know this is a zero force member, let's go ahead and take a look at joint A. Let's assume we didn't know that, okay? Let's take a look at joint A. All right. So what do we know? Here's the joint, member, member. This is 3 to 4 slope ratio. Okay? Now we know our reactions. We know that this 11.1 kips. This is 14.8 kips. Okay? So let's see. Horizontal, vertical, vertical, right? Which one do we solve for first? So if this is 14.8 to the left, this is 14.8 to the right. Right? And then how do we get the vertical? Slope ratio, right? So we say what is that? So if that's 11.1 kips, so I've got 11.1 going up, 11.1 going down, it makes our vertical a zero force member, right? So that's one way we can determine it's a zero force member. The other way is to do what we just did, bringing back all that truss analysis stuff y'all did a while back that I know everybody loves. Okay, so how do I figure out the force in the threaded rod now? Well, we have the X component, we have the Y component. And this ends up being 18.5 kips. By the way, is that a tensile force or a compressive force?
Tension.
That would make sense if we're designing a threaded rod as a tension member. It better be in tension, right? Okay. Pretty easy, right? Okay, so the threaded rod part, the threaded rod design, really easy. So our expression that we're going to use is that. And we need our PU, which in this case is 18.5 kips, because that's what the rod is going to experience. Our FU is going to be 58 KSI, because if you recall, this was A36 steel, okay? A36 steel. So therefore, what is that? Second? So what rod are you going to use? 1 inch?
0.875.
How about a 7/8 inch diameter? Because a 7/8 inch diameter is 0.875 inches. So okay. That's not that hard, is it? We had a nice little structural analysis review and handled a nice little common component in structural steel building applications. All with, I believe, time to spare. I've given you 9 minutes of your life back to work on hydraulics and environmental. That's all I got, everybody. I will see you all next week. I know things about stuff.